So, hello everyone again. This is lecture 7 part 3 of wave optics. In today's lecture we will go on to final discussion of diffraction pattern, and after the completion of diffraction pattern we can go to polarization. So, I am Sameer Lavankar. Let us begin our discussion. So, a course outline. So, we started with the introduction concept of wave optics, moving on to the wavefront concept in Huygens principle. Then refraction and the reflection laws were being proved in the Huygens principle using the third concept of wavefront and Huygens principle. The fourth was coherent and incoherent addition of waves, in which we understood the value of intensity being maximum for coherent addition and minimum for incoherent addition. A small concept of Doppler effect was also being explained in this concept only. Moving on to the fifth concept of interference of light waves in Young's experiment, in which we understood what is interference of light waves, what is this Young's experiment, why was a need of phases to be logged was necessary for Young's experiment to occur. Then what will be the effect on the interference fringes if there is a change in the monochromatic source of light to a white source of light, if we change the value of lambda or capital D or small d, etc. Today we are on the final point of diffraction pattern, and after diffraction pattern is being studied we can go to last point of this discussion, which is related to polarization. So, without wasting any time, let us move on to discussion of resolving power of optical instrument. So, what is the resolving power of optical instrument? So, please look over here carefully, it is one of the important concepts of diffraction. So, consider a parallel beam of light falling on a convex lens. So, as you can see that this is a convex lens being put here. So, let us suppose a parallel beam of light. What does it mean by parallel beam of light? That the light source is very far, let us say it is at infinity distance, and so every source which is coming from it is nothing but a series of parallel lights. So, this is the concept we talked about here. Let us suppose that the parallel beam of light are being incident on this convex lens. If the lens is well corrected for aberration, that is there is no error, that is a perfect ideal convex lens, then geometrical optics tells us that the beam will get focused to a point. So, quite evident, we know from the concepts of optics that if there is parallel beam of light, then it will get focused, all the lines will converge at a point called as focus. So, this is the simple conclusion of if there is no aberration, if there is no corrections to be performed on a convex lens. So, this is the simple concept we understood. However, because of diffraction, so now what does diffraction do? What does diffraction have a part in this? The beam, instead of getting focused to a point, gets focused to a spot of finite area. So, it does not get merged on a single point, it gets focused to a spot of finite area. So, it has a finite area. So, this can be understood like if I try to tell it as a focused area, let me not go into it. So, there is an area for if there is no aberration, then the value of it is focused at a single point, let me note that point as f, but according to diffraction pattern, because of diffraction it is focused on specific area. Sometimes any beam of light can can lock at this position, some can lock at this position, some can lock at this position, some can lock at this position, and similarly if we take a locus of every point we can find a specific area. In this case, the effects due to diffraction can be taken into account by considering a plane wave incident on a circular aperture followed by a convex lens. So, what happens is, if we need to understand this theory, if we need to theorize this concept of why it is not converging on a single point, why it is converging on a specific area which is having a finite area. So, we can understand that concept if we consider these parallel lines of waves as plane waves. So, if these plane waves are incident on a circular aperture followed by a convex lens. So, if we can understand this phenomena, if we take into account the diffraction pattern also by considering a plane wave incident on a circular aperture followed by a convex lens. So, first of all we take a circular aperture and then we follow it by a convex lens. The analysis of the corresponding diffraction pattern is quite involved. However, in principle it is similar to the analysis carried out to obtain the single slit diffraction pattern. So, the single slit diffraction pattern, it is similar with this circular aperture followed by a convex lens. So, let us move on to next slide now. So, taking into account the effects due to diffraction, the pattern on the focal plane would consist of a central bright region. So, as you can see, this is the central bright region we talked about here, surrounded by concentric dark and bright rings. So, these are dark rings, and then again there is a bright ring here. If I explain you like this, so this is the central bright fringe. So, this is central, there is not a fringe here, it is a region here now. So, it is a central bright region, then there is a dark region here, there is a dark region here, and then there is again a bright region here. Okay, so taking into account the effects due to diffraction, the pattern on the focal plane would consist of a central bright region. So as you can see, this is the central bright region surrounded by concentric dark and bright ring. So this is the concentric dark ring and this is the concentric bright ring. A detailed analysis shows that the radius of the central bright region is approximately given by. So now just the memorization part, the analysis, the complete theory or the procedure to get this value is not in your syllabus. So you just need to remember this formula. So the value of the radius of the central bright region is nothing but 1.22 lambda small f upon 2a, or just dividing 1.22 by 2 gives you 0.61 lambda f by a. What is the f value here? F is nothing but the focal length of the lens, and what is 2a here? 2a is the diameter of the circular aperture or the diameter of the lens. So quite evident, so is not necessary to write it again. F is nothing but the focal length of the lens, so f is given to you as focal length of the lens, and a is given to you as diameter, radius. A is the radius of the circular aperture, so therefore 2a will be the diameter of the circular aperture. Typically, so now if it is taking just an example scenario here, so what will be the range of value of small r naught? Then typically if lambda is approximately equal to 0.5 micrometers, small f is equal to approximately 20 centimeters and small a is approximately 5 centimeters, we have r naught is approximately 1.2 micrometers. As we know that the value of micrometer is nothing but 10 to the power minus 6 meters. So you can observe that that point which is not even visible to the naked eye, if we assume, if we understand, if we take even if we take into consideration diffraction effects, that complete area is also very small, then it is not even visible to naked eye. That's why sometimes when we try to explain the concept of optics, we find that it is converging to a single point only. Okay, so although the size of the spot is very small, it plays an important role in determining the limit of resolution of optical instruments like a telescope or a microscope. So even if the spot is small, so quite evident from the line only that it plays an important role in determining the limit of resolution of optical instruments like a telescope or a microscope. So now for the two stars to be just resolved, as in if we are using a telescope and we just need to find out if we want to see a clear image of the moon or let us say stars being talked about, then for that clear resolution what we need is that f delta theta should be approximately equal to r naught. We know the value of r naught which is equal to 0.61 lambda f by a, implying, so similarly we can get delta theta is nothing but, so just deleting or cancelling delta f from both sides, we will get delta theta is approximately equal to 0.61 lambda by a. Thus delta theta will be small if the diameter of the objective is large, quite evident if the value of objective is large. These are all the concepts of your optics only, so I am not going into details of these things. Thus delta theta will be small if the diameter of the objective is large. This implies that the telescope will have a better resolving power if A is large. It's quite evident, as you can see that if the value of A is increased, the value of delta theta is decreasing, and if it is decreasing, the resolving power is increasing. This implies that the telescope will have a better resolving power if A is large. It is for this reason that for a better resolution, a telescope must have a large diameter object. So this is the only case scenario, then that is why we use a telescope which is a large diameter object. Even at the large diameter objective, it is in the range of centimeters only. Okay, so now let us move on to one of the questions of resolving power only. So please look over this question. So assume that a light of wavelength, so wavelength 6000 Armstrongs is given. So as we know that Armstrongs is nothing but 10 to the power minus 10 meters. Okay, so this wavelength is given to you here, wavelength is given to you, is coming from a star. What is the limit of resolution of a telescope whose objective has diameter of 100 inch? So just for your clarity, 100 inch is equal to 254 centimeters, or 1 inch is equal to 2.54 centimeters. So this, if the diameter of objective is given to you, that means 2a is given to you. So please look over this carefully, that either the diameter is given to you in the question or radius is given to you in the question. So here 2a is given to us as 100 inch. 100 inch is nothing but 2.54 multiplied by 100, that will give you 254 centimeters. Now also lambda is given to us, so lambda is nothing but 6000 multiplied by 10 to the power minus 10 meters. So therefore if we need to convert it into centimeters, then it is 6 into 10 to the power 3 into 10 to the power minus 10 into 10 to the power 2 meters, it will give us 6 into 10 to the power minus 5 centimeters. Now resolving power is nothing but the calculation of this. So this delta theta is nothing but the resolving power. delta theta is nothing but the resolving power or limit of resolution. We can like this as limit of resolution. Let us call it limit of resolution only for now, because that will be much clearer for you for now. So, limit of resolution of a telescope whose objective is a diameter of 100 inch. So, if lambda is approximately 6000 Armstrong, therefore delta theta is nothing but simple formula put. So, 0.61 lambda by a, lambda is given to you as 16 × 10⁻⁵ a is given to you as, please make sure if 2a is 254 centimeters, then a will be nothing but 254 divided by 2. Hence, you will get the value of theta in radians, which is equal to 2.9 × 10⁻⁷ radians. Hence, we got the limit of resolution as 2.9 × 10⁻⁷ radians. After this, let us move on to more further discussions on this concept only. So, now we can apply a similar argument to the objective lens of a microscope. In this case, the object is placed slightly beyond f. So, in this case we are assuming, so first of all please look over this diagram here, I will try to explain to you. So, as you can see, this is a convex lens here, an object is being put here, then what more to be understood here, this is that point at which we need to find out the value of image. This is the image being formed on a plane, this is that plane, and this is the resolving power which we got, it is 1.225 f lambda by a, or we can write it as 0.61 lambda by a, f lambda by a, capital D is equal to 2a. Okay, so this being understood, let us move on to the things written on the left. So, in this case the object is placed slightly beyond f. So, just beyond f the object is placed, so that a real image is formed at a distance v. So, this is the distance v being talked about here. The magnification, what is magnification? Magnification is nothing but the ratio of image size to the object size. So, the magnification is the ratio of image size to object size given by small m is equal to capital V by f. So, it is nothing but magnification is nothing but the value of this divided by this value, that is small v by small f. These are all the concepts of your optics only, so I am not going into details of these parts. It can be seen from the figure that capital D by f is approximately equal to 2 tan beta. So, how can we understand this concept here? So, as you can see here, if I try to just use mathematical calculations here, so tan beta is nothing but capital D by 2 upon f. Therefore, D by f is equal to 2 tan beta. And please make sure here it is an approximately sequence, because we do not know the exact sequence of it. Therefore, it is approximately equal to 2 tan beta, where 2 beta is the angle subtended by the diameter of the objective lens at the focus of the microscope. So, quite evident this is that complete angle of 2 beta. So, this is that complete angle of 2 beta. So, when the separation between the 2 points in a microscopic specimen is comparable to the wavelength lambda. So, now we are assuming that this separation between the 2 points is comparable to wavelength lambda, the diffraction effects become important. So, it is explained by the diffraction's definition also. What is diffraction? Diffraction is nothing but the bending of light when it is occurring when the obstacle is approximately equal to the wavelength or in the order of wavelength of light. So, the image of a point object will be again a diffraction pattern whose size in the image plane will be, so it is again similar concept v theta, we know the value of theta, that is 1.22 lambda by capital D. Two objects whose images are closer than this distance will not be resolved, they will be seen as one. So, it is just trying to say is if we try to, these two objects will be merged into one image. The corresponding minimum separation, so that minimum separation which we require so that these two objects are not being merged into similar thing, that d min is nothing but v 1.2 lambda by dm, and the just using similar, this m is nothing but magnification here. So, this magnification we know that is equal to v by f, hence v getting cancelled, we will get the value of d min as 1.22 f lambda by capital T. So, for this case scenario you just need to remember this stuff. There is nothing much more to be explained. These are nothing but simple mathematical calculations after we know the value of resolving power, that is 1.22 lambda by small capital D. Okay. Now combining the above two equations, we get 1.22 lambda by 2d is equal to 1.22 lambda by 2 sin beta. So from above case scenario we got lambda as tan beta, and from this case scenario we can get 1.22 lambda by 2 sin beta. Therefore, if the medium between the object and the objective lens is not air, just assuming, so now even if in the different concepts such as electromagnetic inductions and all, similarly in the ideal case always air is there, but even let us say the air is not visible, then we can find out the value of d min by modification in the formula by just writing a value of n here. So if the medium between the object and the objective lens is not air but a medium of refractive index n, then the equation gets modified to d min is equal to 1.22 lambda upon 2n sin beta. This product n sin beta is nothing but called as the numerical aperture. So just you need to remember this, that n sin beta, because it can be asked in the question directly, the refractive index will be given to you and value of beta will be given to you, and you will be asked what is the numerical aperture. So numerical aperture, please remember this, that numerical aperture is called as n sin beta. Okay, and is sometimes marked on the objective. So objective, so in the objective lens also sometimes numerical aperture is being written. The resolving power of the microscope is given by the reciprocal of the minimum separation of the 2 points seen as distinct. So resolving power is nothing but the inverse ratio, that is 1 by d min here. It can be seen from the above equation that the resolving power can be increased by choosing a medium of higher refractive index. So quite evident, if we need to increase the resolving power of the microscope, the resolving power is the inverse of d min. So if we increase the value of n, we decrease the value of d min, and if we decrease the value of d min, we increase the value of resolving power. So how will I explain this? Let me write resolving power here. So let us write resolving power is inversely proportional to d min, and as d min is inversely proportional to n, that means it is directly proportional to value of n. Therefore, if the value of n is being increased, then that means that the resolving power is also increased. So it can be seen from the above equation that the resolving power can be increased by choosing a medium of higher refractive index. So if a higher refractive index medium is being used, then the resolving power is increased. Usually an oil having a refractive index close to that of objective glass is used. Such an arrangement is also called as oil immersion objective. So this is just a knowledgeable expression here, that usually a oil is having a refractive index close to that of objective glass is used, and such an arrangement is called as oil immersion objective. Okay, so let me stop it here only. So in this lecture we understood the concept of resolving power. What is the resolving power? So for your exam point of view, please remember this circular aperture, that is the radius of circular aperture is nothing but 0.61 lambda f by a. What is f here? F is nothing but the focal length of the lens, and what is a here? A is the radius of the circular aperture. In the questions may be asked regarding this. Then delta theta, please remember delta theta is nothing but known as limit of resolution. If the limit of resolution is asked, it is nothing but 0.61 lambda by a. There is no multiplication of f here. So this is the next concept we understood in this, and then this was the final discussion we are talking about, in which we understood that magnification, these are all the optics concept again, magnification is nothing but v by f, and now we found out the minimum distance, so that those two objects which are very close to each other, the images do not get merged. For that d min is nothing but 1.22 small f capital lambda by capital D. Also final concept which we understood in this, that if we need to find out the value of resolving power, increase or decrease depending on the refractive index, as we know that the resolving power is inversely proportional to d min, and d min is inversely proportional to refractive index. So as the refractive index keeps on decreasing, the value of d min will keep on decreasing. If the value of refractive index keeps on increasing, d min will decrease, and because d min will decrease, the resolving power will increase. So let me conclude it here only. So the course progress for you, we concluded, we understood the concept of introduction, that is wave optics, how it is different from Descartes' theory, then Huon's principle about wavefront, then the proof of refraction, the reflection, coherent and incoherent addition of waves, interference of light waves in experiment is also done. Right now we are on the diffraction concept. After the resolving power of optical instruments is being done, then we will move on to polarization, and after polarization is being done, that is the end of your wave optics. So for now, thank you.